Welcome to this video on Euler-Bernoulli beam theory. This is one of several videos in a short course on structural members posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. Beam theory is a staple of structural analysis. What we call Euler-Bernoulli beam theory is taught in every undergraduate program in civil engineering, mechanical engineering, and probably other disciplines as well. For that reason, it may be surprising that the version of beam theory we use today became widespread only a little more than 100 years ago. In 1638, the two new sciences addressed by Galileo included solid mechanics and an attempt to determine the strength of the beam shown on the right-hand side. Unfortunately, a problem with the location of the neutral axis means that this is not the theory we use today. Not long after Galileo did his work, Marriott established a beam theory that was employed in various forms for the next 200 years. Then, in 1750, Leonhard Euler and Daniel Bernoulli engaged in communication that established the foundation for the beam theory we use today. Specifically, Daniel Bernoulli provided an expression for the strain energy in beam bending, from which Euler derived and solved the differential equation. The work built on earlier developments by Daniel's uncle Jacob. However, it took more than 100 years before that theory became widely accepted. In the meantime, Augustin Cauchy developed the concept of stress in 1822 and Navier extended the prevailing beam theory, which at the time included considerations at the molecular level. It was only with the construction of the Eiffel Tower and the construction of the first Ferris wheel a little over 100 years ago that the present-day Euler-Bernoulli beam theory became widely accepted and utilized. Remember, there is a chronological list of events on the Basics page at terje's Toolbox. One item you will see there is that the very same Marriott who developed the beam theory also discovered the blind spot of the eye, and amazed the French royal court in 1660 with his demonstration of it. We have already seen in another video that a structural member is a mathematical boundary value problem. The boundary value problems for longitudinal type members need to develop equilibrium between the load and a stress resultant, section integration to link the stress resultant with the stress, a material law to link the stress with the strain, and a kinematic compatibility equation to relate the strain at a point with the global displacement. Those equations are established in this video for Euler-Bernoulli beams. The notation employed in terje's Toolbox is shown here. X is the longitudinal direction. Z is the vertical direction, which is the direction of the loading and resulting displacement. Y is the horizontal direction perpendicular to the member. Bending occurs about the y-axis. QZ is the distributed load in the z direction. V is the shear force, which is the resultant of shear stress. M is the bending moment, which is the resultant of axial stress. Iy is the moment of inertia about the y-axis. E is the modulus of elasticity, which we often call Young's modulus. Sigma is the axial stress. Epsilon is the axial strain. U is the displacement in the x direction, and W is the displacement in the z direction. The Euler-Bernoulli beam theory contains an anomaly. The problem is explained with this figure, which shows the contours of the boundary value problem for beam bending. In this video we will walk the path from applied load, QZ, to displacement, W, via bending moment, axial stress, and axial strain. The problem is that shear stress is missing. And without shear stress there is no shear force. However, it will soon become clear that shear force must be present when the value of the bending moment varies along the x-axis. This is a paradox. The formulation of the boundary value problem omits shear stress, but a shear force must be present. The anomaly is solved by adding equilibrium considerations that are outside the formulation of the boundary value problem, in order to recover the shear force. Also, in another short course on cross-section analysis, we will add equilibrium considerations in order to recover the shear stress. In summary, we formulate the boundary value problem for beam bending in terms of axial stress. Then, later, we introduce additional equilibrium equations to recover the shear force and shear stress. The next slide presents one such instance. On this slide, notice that the distributed load, QZ, is in the upwards direction. Also, notice that a shear force is introduced, in addition to the bending moment stemming from axial stress. It is not possible to establish equilibrium for this element without shear forces. This is indeed one example of recovering a shear force that is formally outside the formulation of the boundary value problem, which omits shear stress. Vertical equilibrium is considered first, and results in the fact that the distributed load equals the derivative of the shear force. Moment equilibrium about the rightmost edge, identified as point A in the figure, gives that the shear force is the derivative of the bending moment. Notice the term marked in blue in the moment equilibrium equation. It accounts for the fact that the resultant of the load on this infinitesimally small element is Qz times dx. The moment arm is dx over 2. As a result, this term contains dx squared. That leads us to neglect this term, because dx squared is a so-called second-order term that is sufficiently small for us to omit. On the next slide, we consider section integration. Integration of axial stresses over the cross-section is expressed in the equation at the bottom of the slide. The minus sign appears because it is compressive negative axial stress in the positive domain of the z-axis. It is exactly compressive stress at the top that gives what we here consider a positive bending moment, namely, bending moment with tension at the bottom. In short, sigma is negative where z is positive when we work with a bending moment that gives tension at the bottom of the beam cross-section. The figure is included to explain that point. The minus sign in the section integration equation is necessary in order to get the moment shown with semicircular arrows on this slide. The material law adopted in Euler-Bernoulli beam theory is simply Hooke's law. That means the stress is equal to Young's modulus times the strain. We can make an additional point here, for the viewer who has been exposed to more of the theory of elasticity. In the context of two-dimensional theory of elasticity, the use of Hooke's law shown at the top of this slide implies a so-called plane stress material law. That implies that there is zero axial stress perpendicular to the beam, in the y direction. That makes sense for relatively narrow beams, but not for beams that are so wide that they can be considered a plate. The alternative plane strain version of the two-dimensional Hooke's law is more appropriate in that case. In that case, it is not the stress that is zero in the y direction but rather the strain. This equation shows how the strain is restrained to zero in the y direction. Notice that this is the two-dimensional version of Hooke's law, and notice the appearance of Poisson's ratio, denoted by the Greek symbol nu, to include the transverse strain. The result is that we now have a stress perpendicular to the beam, denoted by sigma yy. Next, at the bottom of the slide, we substitute what we just found into the material law in the x direction, again using the two-dimensional version of Hooke's law that includes transverse strain. The result on the right-hand side shows an alternative version of the stress-strain relationship compared to what we started with at the top of the slide. It shows that for wide beams and plates, we should use E over 1 minus nu squared instead of just E. On the next slide, we address kinematic compatibility. The relationship between the axial strain, epsilon, and the transversal displacement of a beam, W, is sought. It is first recognized that bending deformation essentially implies shortening and lengthening of the fibers of the cross-section. Fibers on the tension side elongate, while fibers on the compression side shorten. For that reason, the starting point on this slide is to link the axial strain to the change in length of the imaginary fibers that the cross-section is made up of. For that purpose, we employ the same consideration as we do when we establish kinematic compatibility of truss members, namely that strain is change in length divided by original length. That equation is shown in the top left corner. Next, the axial displacement, U, is related to the rotation of the cross-section. Consider the infinitesimal counterclockwise rotation d theta of the infinitesimally short beam element shown here. Keep in mind that we call this rotation of an infinitesimally long beam element for curvature, because d theta is change in rotation per unit length. Under the assumption that plane sections remain plane and perpendicular to the neutral axis during deformation, which is referred to as Navier's hypothesis, each fiber in the cross-section change length proportional to its distance from the neutral axis. The amount of shortening or elongation depends upon the rotation of the cross-section. A geometrical consideration of this figure reveals that the shortening and lengthening, namely the axial displacement, u, of each infinitesimally short fiber is d theta times z. The minus sign appears because the u displacement is negative where z is positive. Next, the rotation, theta, is related to the transversal displacement, w. For this purpose, consider 2 points on a beam that is a distance dx apart, as shown in the figure on the right-hand side. A line through those points identifies the rotation of the beam at that location. The relative displacement is dw, which is positive upwards. Because we say that counterclockwise rotation is positive, we find that theta is dw over dx. In other words, the rotation is the derivative of the displacement. The tangent function in the formula on the left-hand side is mathematically correct when we consider the triangle that has dx and dw as two of its sides, but we assume small deformations, so the tangent of theta is approximately equal to theta. Combination of the previous equations yields the kinematic compatibility equation for beam bending, namely that the strain is the double derivative of the displacement, w, times z. Notice the minus sign that appeared earlier in these derivations. The kinematic compatibility equation that we now developed implies an approximation of the exact curvature of the beam. Mathematically, curvature is defined as 1 over the radius of curvature, as shown here. In the Euler-Bernoulli beam theory that is presented in this video, the curvature is approximated by the second-order derivative of w, as shown here. Notice that there are two approximation signs. The first alludes to the fact that differentiation is carried out with respect to the x-axis. Unless the deformations are negligible, this is inaccurate. Differentiation should be carried out with respect to an axis that follows the axis of the curving beam. The second approximation is due to our replacement of tangent of theta with theta itself. If we avoid that approximation, then the rotation, theta, involves the inverse tangent function, as shown here. If this expression was utilized in the derivations above, then the differentiation of the inverse tan function yields the fraction shown here. This curvature expression reduces to the one used earlier in this slide when the slope dw over dx is small. It needs to be said that the more accurate curvature expression that we developed at the bottom of this slide is still approximate. That is because the differentiation is carried out with respect to the x-axis and not the axis of the curved beam. From mathematics, the exact curvature is the rightmost expression on this slide. The next slide provides a summary of the equations that we derived in this video. The equations are also combined into the complete differential equation for beam bending, which is marked with green in this figure. The moment of inertia has been defined, shown in the expression identified with a blue color. In the development of this differential equation, it has been assumed that the cross-section is homogeneous so that the Young's modulus, E, is constant. For composite cross-sections, this assumption is not valid. The more general differential equation for beam bending is shown at the top of this slide, marked with the red color. However, there is another way to deal with this problem. For composite cross-sections, one approach is to first retain the original differential equation and then to select a reference value of the Young's modulus. Now, assume that all parts of the cross-section have that E value. Then, the width of each part of the cross-section is modified if its Young's modulus is different from the reference value. The change in width is proportional to the difference in E value. For example, if E is twice the reference value, then the width should be doubled. If this procedure is followed, then the equations marked with green and blue on this slide can be employed without modification. The next slide addresses the solution to the differential equation. Although the differential equation for beam bending is rarely solved in everyday engineering, it is a simple exercise, which is instructive for the study of reference cases. Also, the solution of the differential equation is the starting point for the selection of shape functions in the finite element method, which is covered in another short course at terje.civil.ubc.ca. Toolbox. The shape functions used in the finite element method are often approximate, while the solution to the differential equation reveals the exact deformed shape. In other words, the exact solution to the differential equation for beam bending reveals whether the finite element shape functions are exact or not. The general solution is obtained by integrating 4 times, here assuming that the load, QZ, is uniformly distributed along the beam. We see from the result that under uniform load the displaced shape of a beam is a fourth-order polynomial. Without distributed load, the displaced shape is a third-order polynomial. To obtain the solution for a specific beam problem, it is necessary to specify boundary conditions. To prescribe a rotation, shear force, or bending moment, the following equations are useful. They are obtained by combining certain sets of the equations we established earlier in this video. Remember, the 4 boundary conditions we need in order to determine the constants C1 to C4 all need to be boundary conditions on the unknown displacement, W. For example, if you want to specify the value of the bending moment at a particular point along the beam, for example at one end of the beam, then this equation comes in handy. It shows that a value of the bending moment is enforced by setting the bending stiffness, EI, times the second-order derivative of the displacement, equal to the prescribed value. The final slide is included simply to remind us that there is more work to be done before a beam is fully analyzed. In this video, and in this short course on structural members, cross-section analysis is not covered. That is done in another short course on terje.civil.ubc.ca. Toolbox. In that course you will see that the determination of the cross-section constant that we call the moment of inertia, and the determination of the axial stress in the cross-section, is the easy part. It is the determination of shear stress that will capture most of our attention in the cross-section analysis. That exercise involves the so-called shear flow and the determination of the shear center of a cross-section. To do that for both open and closed cross-sections will be addressed in the short course on cross-section analysis. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.